So hi, my non-existent audience. So, so let me start discussing the solutions to assignment 4. Okay, and once we are done with these questions, I'll summarize what we have done till now in the course at the end. Okay, so so the first question is we have a non-negative random variable z or z, and alpha is a constant, a positive constant, and we want to compute this quantity entropy of alpha z. Okay, so now recall that entropy of alpha z is defined as expected value of alpha z log alpha z minus expected value of alpha z into log of expected value of alpha z. Okay, and this quantity is always positive. This is true by Jensen's inequality. And Jensen's inequality holds because this function fx equals x log x is a convex function. Okay, and this function is defined for x greater than equal to 0, where for x equal to 0 is set it to 0. Okay, so so now we are asked to, okay, so for instance, if we have this variance, so variance of alpha z, we know that this is alpha square into variance of z. Okay, so now we want to do a similar thing. We want to find out a similar property for the entropy. Okay, so now if we just, so we have this expression, and now we just if we just take, so this would be alpha into, you can write this as expected value of z log alpha z minus expected value of z log expected value of alpha z. Okay, and then you can write this as log alpha plus log z, right? And similarly, this would be log alpha plus log expected value of z. Okay, because the alpha comes out, and okay, so this then becomes alpha into so expected value of z log alpha plus expected value of z log z minus log alpha into expected value of z minus expected value of z into log expected value of z. Okay, and so this expected, so this log can come outside because it's a constant, and so this gets cancelled with this, and so basically we are left with alpha into expected value of z log z minus expected value of z log expected value of z. Okay, which is just alpha into entropy of z. Okay, so unlike the variance where this alpha square comes out, we have alpha here for entropy. Okay, so option D is the correct one. Okay, and other options are not true in general. Okay, so question number 2. I think these questions are not in the same order as on the portal, so yeah, just bear with me. So question number 2 here is, let x be a real valued random variable and let pq be distributions such as dq by dp of x is g of x. So again, this is known as Radon-Nikodym derivative, right? Radon-Nikodym, this is just so that when you see this name, you're not terrified. So Radon-Nikodym derivative of q with respect to p. Okay. So when q and p are discrete random variables, this is just a ratio of like qx by px. So suppose, right? So this is q, where small q is PMF of q, and the small p is PMF of this distribution p. Okay, so, and this is also true for when PDF exists. So this could be either PMF or PDF. Okay. Yeah, so this is what you mean by dq by dp. And G is a non-negative function. G has to be a non-negative function for it to define a probability density. And because Q and P are probability densities distributions, which of the following are true? So, okay, so this is the standard property of this thing, that this is basically the definition of dq by dpx. Um, so suppose we want to compute some random variable, expected value of some random variable with respect to P, with respect to Q. Okay, so we can do this. And suppose like computing expectations with respect to P is easier. So what you can do is, uh, you have this X, okay, but since you are changing your measure, so by measure I mean this probability distributions, right? You have to multiply this X by something, and that is this Radon-Nikodym derivative. Okay, so what this Radon-Nikodym derivative thing tells you is that there exists a function, right? There exists a function from, say, this X, script X, where X takes value to positive real numbers, okay, such that this expression holds, and that function we denote by dq by dp. Yeah, that's it. That this is just a notation, dq by dp. There is no like differentiation going on here. Okay, and there's a reason for this notation, makes things uh, easy to see. So um, yeah, it makes things easy to see in this sense. So what would be this? This is basically, if you write it in this measure theoretic sense, this is just, right, you are integrating X with respect to this measure Q. Okay, right, this is just notation for that. And on the right side, you are again integrating X dq by dpx with respect to the P measure, right? And so, right, you can see that this dp and dp cancels, right? This is a bad way of seeing, but this is basically dq of X. So right hand side and left hand side are equal, right? So this is the reason for this notation dq by dp for this Radon-Nikodym, and this is why it's not a Radon-Nikodym derivative. All right, so okay, so this is the main property. This is the defining property of Radon-Nikodym derivatives, and right, and this we know this is given to be like g of X, and so yeah, which means, so option B is correct, option A is not correct. Okay, and this again you can see. So if you just take X equals 1, right, or X equals, yeah, 1, which means that this random variable is a constant random variable throughout the domain. Its value is 1. Okay, so I'll just write like X equivalent to 1. So this, because X is a function on sample space, and 1, I'm treating 1 as a function on a sample space where the value is 1 at all the points in the sample space. Okay, so then with respect to Q, if you take, you'll have this expected value of 1, and on the right hand side you will have 1 into dq by dp of X, right? And we know that so this 1 is a constant random variable, so its expected value is 1 with respect to any distribution, any probability distribution. Okay, so what we have shown is that 1 is equal to expected value of g of X. Okay, so this is, which is option C. Okay, so if you take the Radon-Nikodym derivative of Q with respect to P and integrate it with respect to P, you get 1. Okay, so this is yeah. So this was question number 2. Okay, question number 3. So now, yeah, this involves, okay, so this, let's say this what the question is. So let X and Y be discrete or countable sets. Okay, so let X, Y be random variables, P X Y Q X Y be joint distributions. Okay, so again we, Q and P are related like this through this Radon-Nikodym derivative, right? And G is a, where G is a non-negative function. Okay, this is standard. Let P given X, Y given X, and P given P, Y given X denote conditional probability of Y given X. Okay. So which of the following are true? Okay. So first this notation. So we know. Okay. So what is this Q Y given X? Okay. When you write just this expression Q Y given X, this basically represents a class of probability distributions, a set of probability distributions. And what I mean by that is that for every x equals x, so whenever you fix x to a fixed value, a particular value, we have a, a probability distribution. Okay, we denote this probability distribution by this q. Okay, so this is a probability distribution on this y set. Okay, so for fixed x, you have this conditional probability distribution on y, which is denoted by this notation y given x, right? But you are since fixing one particular x, yeah. So for every x, you have a distribution on y. Okay, this is what it says. Okay, so yeah, so we want to compute the Radon-Nikodym derivative of this conditional probability distribution. So we are given the Radon-Nikodym derivative for the joint probability distribution. So we have this dqxy by dpxy x comma y. Uh, we are given that this is g x comma y for some function g, right? And then we want to compute dqy given x by dpy given x y given the small x. Okay, so once you fix small x, this dqy given x and dpy given x become probability distributions on the set y, the script y where y belongs. And then yeah, for a fixed y, what is it? What is the value of this derivative? Okay, so since these are like discrete probability distribution, these will have PMFs. Okay, probability mass function. And so okay, so let me denote. So let q x comma y be PMF of q x y, and similarly p x comma y PMF of p x y. Okay, probability mass functions. So now we want to compute, right? So then what this ratio, what this is asking is, you have q, okay, of y given x by p of y given x, right? You basically want to compute this quantity. So like I said, so this gxy is, since the PMFs exist, in this case it's just q x comma y by p x comma y, and we want to compute q y given x by p y given x. Okay, so then, so what is this? So we can apply Bayes rule. So q y given x is what? It's q x comma y by q of x. Okay, similarly, py given x is p x comma y by p of x. Okay, so what we have is q x comma y by p x comma y to px by qx. Okay, so yeah, so we know what qx comma y by px comma y is. It's just gx comma y. So this quantity is gx comma y. Okay, so, and now we want to see what px by qx is. So let's see what px by qx is. Okay, or let us compute qx by px, since yeah, we want to compute a denominator. So qx by px is what? So one way to write qx is just write qx as uh, summation over y qx comma y, right? And yeah, so okay, let me just okay, just qx is summation of y qx comma y, which can also be written as px comma y into gx comma y, right? And this is from here. Okay, so by definition of Radon-Nikodym derivative, we have that qx comma y can be written as this, and this can again be written as, you can just px comma y. Okay, and now you have this px in the denominator, right? And so basically what we obtain is qy given x by py given x is gx comma y by summation over y px comma y gx comma y by px. Okay, this by px is because we have this by px here, which is basically gx comma y by, okay, so what is this? This is just p of y given x. Okay, so it's like p of y given x into g of x comma y. Right, so this means this option A is correct, and again B, C, D are not correct in general. So okay, so what this means, okay, so let us see what this means. So we were given this Radon-Nikodym derivative of the joint distribution function, and we found a Radon-Nikodym derivative for this conditional distribution function, and the Radon-Nikodym derivative turned out to be this, which was like gx comma y by expectation of gx comma y. This is basically what this is, expected value of g x, where x is fixed to small x, and this y is varying, and y is coming from this density function, which what is PMF, which is like, right? So you are given x, y is y is basically conditional distribution given small x. Okay, so this is the Radon-Nikodym derivative for the conditional distribution. Okay. So the next question, consider the same setup as in question 3 above. Wait, what is question? Oh, this question, yeah. And which of the following are true? Okay, so now we want to compute. Okay, so the same setup as in question 3 above. So we know that these are discrete distribution, discrete probability distributions, and gxy is dqxy by dpxy x comma y, right? This is gxy. Okay. And we want to compute this the KL divergence. So KL divergence between qxy and pxy. So by definition, this is, write it in two ways, but okay. So this is expected value where x and y are coming from this qxy, and then this log dqxy by dpxy x comma y. Okay, this is the definition. Let's treat this as a definition of KL divergence. And now, okay, so this was, we are taking expectation with respect to with respect to q. Okay, and suppose we want to take, we can write this same expression as, this is also equal to expectation of x comma y coming from pxy. Okay, so now look at this Radon-Nikodym derivative. We wanted to compute something with respect to q, and now we want to write it in terms of this base distribution. Okay, this p, the denominator, and so what we do is we write whatever we want to take expectation of, which is this Radon-Nikodym, log of Radon-Nikodym, times the radon nicotine derivative. Okay, let's come on. Right. So yeah. So this is a definition of K divergence. Okay. So if you see option A corresponds to option A corresponds to this equality, and option B corresponds to this equality. Okay. So in option B, gx comma y log gx comma y, right? So this, because this is gx comma y and this is gx comma y. Okay, and you have summation over this px comma y because we are taking expectation over px comma y. Okay, and similarly for option A. So option A and B are correct. Okay, now we need to prove some inequality. So in this week's lecture, we derived some chain rules on KL divergence. Okay, so one of them was that if you want to compute KL divergence of these KL divergence between these joint distributions, you can break it as KL divergence between these marginals plus, okay, so you have the scale divergence between x and qx and px, and now we will compute scale divergence between y given x and py given x. Okay, but like I said, for every fixed x, this would give one scale divergence, and we want to do it for all, like, okay, so that is why there is an expectation over x, and where x is coming from the first distribution q of x. Okay, this is the chain rule we derived. You could have also written it as like d q by py plus than d x given by and p x given by. Okay, so basically you could have interchanged the roles of x and y. Right, and we also saw in the lecture, and that came from this basically concavity of the log function, and then using Jensen's inequality, that KL divergence is a positive quantity always. Okay, if you're taking, I mean, if you're taking between distribution function, and so this is a quantity greater than 0 for every fixed x, right? And so the expected value would also be greater than equal to 0, right? So which means this option C is correct, that since the second term this second term is greater than equal to 0, if you drop that, right, you will have that dqx y pxy is greater than equal to dqx px. Okay. Yeah, and there are many ways of writing this chain rule. I mean, you can rewrite this in many forms, and one of the forms again we saw was that this is again equal to dqx px plus yeah, so so what is happening in the second term? So in the second term you have this x, which is a random variable, and then once you fix x, this y would be a random variable, and there would be again an expectation over y given x, right? Q of y given x, when you're computing the KL divergence in the definition of KL divergence. Okay, and so what you can, I think this was also done in the lecture, but whatever. So like x comma y, you can write it as an expectation over the complete joint distribution. Okay, and just this log of q y given x p y given x. Okay. Okay, so the notation can be a bit messy, but this y given x in the subscript, this is nothing. Okay, this is just a notation that we are dealing with conditional. The xy which you are sampling will actually go in this parenthesis here. Okay, you'll compute appropriate conditional probabilities and then do this. Okay, so D is saying, okay, so now this term is greater than equal to 0 again, right? Because it's a scalar. And so we should have that dqxy pxy should be greater than equal to this term, right? And this equality is the reverse of that, the inequality in D. So D is an incorrect option. Okay, let's go to question 5. So question 5 is, we are given two Gaussian distributions, and we want to compute their K divergence. Okay, so P is what? P is basically, this is normal of, okay, 1 1 1 1 1, how many times? D times, into this identity covariance matrix, right? And Q is -1 -1, and again this identity covariance matrix, right? These are d-dimensional uh, matrices and vectors. Matrix is D cross D, and vector is a d-dimensional vector. Okay, so D cross D. And we want to compute the K divergence. Okay, so one way to compute the K divergence would be what? Let's write the formula for K divergence. Okay, this is, suppose this X is sampled from P. We want to compute log dq, sorry, log dp by dq of X. Okay, this is, we saw earlier, that is the first thing. Right, you take expectation with respect to the first thing, and then only the log is inside. If you want to take expectation with respect to the base thing, the second argument, then you have to multiply with this identical derivative. So either definition is okay, but we are working with this. So now we know what the density function looks like. So I mean, this is a normal probability distribution, so density function exists, and dp by dq of X would just be this multivariate normal density function, right? Which looks like, yeah, which looks like something. So you can compute that, that wouldn't be very difficult. But there is one more observation which you can make, which is that, so X here is d-dimensional, right? This is multivariate Gaussian, and all. Okay, so now we know, I mean, we saw it in the lecture, and we can derive it using the chain rule for K divergence, that this is just dpi qi. Okay, so suppose Pn is like P1 product distribution, n independent product. I mean, this is a product distribution, so n independent random variables distribution for n independent random variables, x1 to xn, where x1 is distributed as P1 and xn is distributed as Pn. And similarly, Qn is this, okay, product distribution again. So in this case, when, so both are product distributions, we can just do this pi qi. I mean, we can take K divergence between each individual coordinate and just sum those, right? So that's what we'll do. So here each individual, so, and we can do that because P and Q are product distribution. P and Q are product distributions because the covariance matrix is this identity covariance matrix, which means that all the coordinates, all the d coordinates are independent of each other. If they were not, you could have used, I mean, you still could have used the chain rule, but they would be like conditional probabilities, like here, right? Q of y given x. Or you could also have computed directly, written the probability density functions of P and Q and just computed this integral directly. Okay, so which means this d in our question, dpq, is just d times K divergence between this one dimensional Gaussian function. It means 1 and -1, and variance is 1. Okay, right? Since all these coordinates are 1 and all these coordinates are -1, basically pi and qi are equal for all i's. Okay, so here n is like t in our question. So this just becomes d times this, and now this is like a single variable thing, and we can easily write PDFs. So what would be this? So suppose I take this as say P1 and take this as Q1. And, okay, so log dP1 by dQ1 of x. Okay, now this x is, I'll write x1 so that you know that this is scalar valued random variable. Okay, so this would be log of, okay, you know what that density is, right? For we have this e power minus x minus mu the whole square by 2, 1 by root 2 pi. So 1 by root 2 pi will cancel when you write this because there's a ratio here of p1 and q1. So it would just be e power minus x minus 1 the whole square by 2 by e power minus x plus 1 the whole square by 2. Okay. This would be just log e. So this x square factor will cancel, 1 factor will cancel. It will be like 2x, okay, which is 2x, right? This is x1, this is x1, all of these are x1. Okay, so now what is, so basically we want to compute, suppose x is coming from, or x1 is coming from n1 comma 1, what is the expected value of 2x1? This is 2 times expected value of x1, and expected value of x1 is just 1 because x1 is coming from n1 comma 1. This is 2. So the total KL divergence then becomes dpq is 2d. Okay, which is option D. C is incorrect. Option B says it's less than equal to 2 square. Okay, so yeah, square root d is smaller than d, and so KL divergence is bigger than. So this is again incorrect. This is just 2, which is wrong again. Okay. Okay, so question number 6. Let Z be a random variable with distribution P. Let PT be the distribution given by. Okay, so we are defining a new distribution PT by defining this Radon-Nicodemus derivative. Okay, which is enough to define the distribution. So we are defining Radon-Nicodemus derivative with respect to P here. Okay, so which of the following are true? Okay, and this is related to this the lecture on Hertz's argument, which related this log moment generative function to KL divergence in some way, right? Uh, entropy of the log moment generative function to KL divergence. Okay, so let's see this. So what would be the KL divergence between dpt and P? Okay, this is just this expected value of x, and yeah, let's say P. We are taking with respect to P since we are given only the Radon-Nicodemus derivative. So yeah, we'll just write this as, so this, okay, let's take this as z coming from P, dpt by dpz into log dpt by dpz. Okay, and we know that this is, so this is just to, I'll write ep here so that you know that z is coming from P, and it's just e power tz by, I'm just substituting this thing here which is given in the question. Okay, times log of e power tz by, okay, right. All right, so okay, so let's, so this is what the KL divergence is, but let's see what's on the right hand side. So it's d by dt of log ep dz by t. Okay, so let's differentiate it with respect to t, and we'll take the derivative inside expectation. Okay, we can interchange expectation and derivative in this case. I don't know, but yeah, you can do it. I mean, these are pretty regular uh, situations here. So we have this continuous function, these bounded things, and so on. Okay, so we can do it. So let's apply the chain rule of derivative. So first, we just keep this as constant. I mean, just fix this and differentiate 1 by t, which gives us minus t square, 1 minus 1 by t square. Plus, we just fix 1 by t and differentiate the other thing. And then we'll have to apply. Okay, this is not chain rule. This is product rule. Okay, product rule. I mean, technically speaking. And now we'll apply the chain rule, which is when we want to compute derivative of this thing. Okay, chain rule is for when there is a composition. So it's a composition of, this is a function of t, where first we take expectation e power tz and then we apply log, right? So we apply chain rule. So this is just ep. Okay, this is because of the log thing, because log of x, derivative log of x is 1 by x. And then we take the derivative thing. We are deriving, we are differentiating with respect to t, and so this z would be treated as constant inside, and so z comes down. Yeah. Okay. And now, yeah, let's do this thing where we take an LCM t square dz, and what we get, first we consider the second term there, so that has a t missing, so there would be t here, and we have minus. Now consider the first term above, which is what is missing there. Okay, this entire thing is missing, so all right. We can take this t inside, right? So basically what we have is that we have this expected value of e power tz log e power tz, right? So I'm taking t inside and then writing tz as log e power tz minus expected value of e power tz log expected value of e power tz by this quantity. And this thing is recognizable. So the above thing is entropy of e power tz. We have 1 by t square. And then on the denominator we have, okay. Now in the first question of this assignment, I mean in this thing we were discussing today, we know that entropy of alpha x is just alpha entropy of x, right? So we can take constants inside, outside entropy, nothing else. So I'll take this constant inside. So this is e power tz, and I mean this expected value is a constant, right? So right. Okay. Now I think this was done in the lecture, and you can verify that this turns out to be, this thing is just the KL divergence between PT and P. Okay, where PT is defined using this expression as the Gradon-Nikodym derivative. Okay, so what we have is what do we have? Yeah, so this derivative is basically 1 by t square d pt p. Okay, let's see the answers. Okay, there's a 1 by t square missing in the options. It should have been like 1 by t, should have been like dp by t square. Okay, this is what we obtained right now. So right, so A is correct if we include this t square factor, otherwise it's wrong. Okay. Um, yeah, the second option is what? It's just log expected value. The thing inside the bracket is expected value, and then e power tz, right, into e power t minus, right, so this is by t. Right, so you can basically do the same thing again. You can do this same derivation again throughout. Okay, so what will happen? Yeah, I don't know why I wrote this. Let me remove it. Let's do the same thing again, except that instead of z, you will have, so option B would be, instead of, so this would be like entropy of e power t z minus expected value of z by expected value of e t z minus expected value of z. Okay, just replacing z by z minus expected throughout this derivation throughout here. Okay, which gives us this. Okay, and you can see that this, yeah. So by this property of entropy, where entropy is constant, where constant times entropy is entropy times, no, where entropy of alpha x is alpha entropy of x. Okay, using that property, you will just see that the constants from both numerator and denominator cancel. So what you will have is this is just equal to e power tz by e power tz again. Okay, right? And when I'm saying constant, I'm including this t as a constant here, and this thing would be a constant. E power t expected value of z would be a constant, and there will be e power t expected value of z constant again from the numerator, right? So I think they'll cancel here, so you don't need to use this property. But yeah, basically b is also true. Again, b is true if you include this t square factor, which I think there's a typo. I don't know if there's a typo on the portal, but at least in my thing there's a typo. So yeah, so I'll put a tick mark like this, just like subject to typo. This is correct. Okay. Um, okay, so C and D. Okay, so now once you have this, again, I think all these were done in the lecture, but yeah, I'm doing it again because it's important. So let's do this. So let's see what option C says. Okay, so option C. So we'll use this. We'll use option A. So it says that dpt p by t square. So by A, we have this is dy dt of that thing. Okay. Now we integrate this on the right and left from 0 to lambda, and again from 0 to lambda, right? So this side we get this expression on the right hand side. I mean, we don't get it yet, but okay. So this part will be covered, right? And d by dt, and since it's inside the derivative, and like there is a dt, so what will happen is that this would just be equal to log expected e power tz by t, right? 0 to lambda. Okay, so the thing in the bracket that becomes the integral, and then you have to compute that integral on the limits lambda and 0. Okay, so now if you compute it on lambda, you get, okay, so for compute it on lambda, you get like log e power lambda z by lambda minus, so you cannot just substitute 0 here, you have to take limit t tends to 0 because yeah, the numerator and denominator both are going to 0. So it's well, it might be, yeah, there's a possibility that it's well defined. So let's see if it's well defined. So now this thing, this is just the derivative of the function g of t at t equals to 0, where g of t is is log e power dz. Okay, and in so this is g of t, right? I'll start writing in red now. So this is g of t, and if you just take the derivative at 0, derivative at 0, this will turn out to be expectation of z. Okay, expectation of z. And so now if you just substitute this here, okay, substitute this expression here, what you get is option D. So option C is wrong. If z were a zero value, a zero mean random variable, C would have been correct. But since we are not given that z is a zero mean random variable, D is correct. Okay. All right. Now question number 7. Given a random variable z, suppose this happens. Okay, so this we'll do this from scratch, just so you recall what Chernoff method is. Okay. So Chernoff. Okay, so we want to compute what? This probability of z minus expected value of z greater than equal to t. Okay, this is less than, I mean, yeah, in this case, okay, this is just equal to probability that 2 times z minus expected value of z is greater than equal to 2t. All right, just multiplied by 2 on both sides. So now in the general Chernoff method, we multiply by lambda, but here we are multiplying by 2, and then taking lambda equals 2, and then this would be less than equal to probability that e power 2 z minus expected value of z, this is z, not 2, okay, is greater than equal to e power 2t. Okay, so I mean, if this happens, this implies that this happens. Okay, so the smaller thing always implies the bigger thing. So if you are in the smaller thing, it implies that you're in the bigger thing as well, right? So that is why when implication is like this, we have an inequality here like this. Okay, we're taking probability of a larger set. Okay, uh, and if the implication holds for the other side as well, in that case we'll have this equality here. But yeah, we don't care about that for now. So okay, so now what? Yeah, so now we apply Markov inequality, which just says that this is less than equal to expected value of 2 z minus expected value z by e power 2t, and we are given that this expected value is less than equal to 3. So basically we have this 3 e power minus 2t. Right, so Chernoff method is very simple if you just fix a lambda and do it. All that complication of maximizing, minimizing comes because we want to choose the optimal lambda. We basically choose lambda depending on t to make this bound as tight as possible. But you can all fix any lambda and derive some inequality. So here we were given this thing, right? With this 2 lambda equals 2. So we just did everything for lambda equals 2, and it was just nothing to do with this. You get this exponential concentration, which means this option, why is this? The option C is correct. Okay, C and D are a little confusing. So C is correct, D is wrong. D is saying you're decaying at a faster rate. Okay, so this may not be correct. If it were like minus t, then we could have ticked D as well. That okay. If it's decaying as minus 2t, it might decay as minus t as well. Okay, but yeah. D is saying that okay, it's decaying like sub-Gaussian, in a sub-Gaussian manner. So that is faster than exponential. A is variance of this thing. So this is basically the second moment. So let y equals e power z minus expected value z. So variance of y, we want to find out what that is, but we are given that expected value of y square is less than equal to 3. So this implies that variance of y has to be less than equal to 3. Okay, variance is smaller than the second one. So A is incorrect. Question 8. So let f be a differentiable function. Let g be defined as gx equals e power lambda fx by 2. Okay, so G, okay, again it's R into R function. Which of the following are true? So okay, we just want to compute the gradient of Gx. So Gx is given as e power lambda fx by 2. We apply chain rule, compute gradient of Gx. Okay, so for chain rule, first we treat this exponential function. I mean, we take derivative of this exponential function, which gives us this lambda by 2 e power lambda fx by 2. And now we take derivative of the numerator of exponential, okay, which, so okay, what do we do? We first take this with respect to x. We have this lambda by 2, and now we take the derivative. So we have this grad of fx, right, in lambda by 2. Okay, so yeah, this lambda by 2 is okay. So we have this thing here, and now so this will be gradient of x, okay, by chain rule. And now what is this? Okay, the second option. Okay, if you want to compute the second norm of this, right, what do we get? We get lambda square by 4, okay, um, e power this lambda fx by 2 the whole square, I mean by 2 the whole square, okay. So because of that, this 2 will go away, and into this, the only vector quantity here is this, okay. So this is a scalar thing, I mean the new, okay, everything, yeah. So this thing is scalar because fx is scalar and everything is scalar. The gradient of fx is the vector, okay, right. So yeah, so we have b and d as, yeah, so b and d would be the correct options. A and C would be wrong. Okay, right. So yeah. So question number 9. Let x1 to xn be random variables. Okay, with distribution p of xn for every differentiable function g. Okay, so we are given this. This holds for all g's. Okay, all differentiable functions. Uh, and then we are given that there is a function f for which this happens, which of the following are true. Okay, so we want to prove some concentration inequality for f of x1 to xn. So what we can do here is that, I mean, the only thing we know as of now is to bound the moment generating function. Okay, so and to relate it to lectures, I'll just, so we want to bound this expected value of e power lambda f of xn minus, okay, where this xn denotes this x1 to xn, right. So we want to bound this, and yeah, and we somehow want to utilize this thing that this p satisfies this variance of g less than equal to this. Okay, so for that, what we'll do is let g, we are now defining a function. Let g of x n would let g of x n be uh, e power lambda by 2 f of x n. Okay, right. And so what would be, so the, okay, so then we have, okay, and yeah, so I'll take this x n as random variable. Okay, this had to be a random variable, this inside expectation. So okay, so this, yeah, and let's call this y. Okay, so then from what from what is given above, from here we have that variance of y is less than equal to 4 times. Okay, so we have already seen this kind of g before, right? And we know what gradient of g of xn would be, right? It would just be lambda square. Uh, where did we see g before? Okay, in this question. So it would just be lambda square by 4 times what? Times e power lambda, right? It's like fxn minus expected value of fxn into this grad of x. Okay, okay. So this would again be into this norm of fxn minus expected value of fxn. I mean grad of this whole thing. So the right. So we are taking like grad of some f minus a constant, right? So derivative of constant is 0. So this is just basically norm of gradient of f. So this is just like lambda square by 4 e power lambda whatever, and then grad of fx. So in the whole square. We know that this is less than 1, which is given to us. Okay, so basically what we have shown. Okay, so now expected value. So expected value of grad g of x the whole square would just be less than equal to lambda square by 4. Okay, this is coming from here. Uh, expected value of e power, sorry, this is lambda by 2. Oh, this is lambda square by 4. This is, yeah. Okay, so this is just e power lambda f minus expected value of f. I mean, yeah, ignoring x for now, which is like lambda square by 4 into 4 into, this is just expected value of y square. Okay, we defined y as this. So there is no 2 here, which means we have taken a square of y and then this expectation here. Okay. So now again we saw in I think last week's last lecture, we saw that if you have this kind of condition that variance of y is less than equal to lambda square by 4 times v times expected value of y square, where y is where y is this. Okay, so then this means, let me write that entire fxn minus xn as just said. Okay, then this implies that expected value of lambda z is less than equal to uh, yeah, it was, what was it? It was like expected value of 1 by root vz. This is less than equal to 16 by 9, which is less than equal to 2. Okay, so this was last week's last lecture. Uh, and we used for, yeah, okay, so let's not go to it. So, right, so which means, so, okay, we have seen a similar thing before. So if this happens, 1 by root v is some constant. Okay, so here that constant is v is 4. Okay, and we just saw what happens in question number 7. Right, we have this expected value of some constant 2, z minus is less than equal to 3, right? So similarly we have here, so this would give a concentration inequality of uh, yeah, so we'll have this 2 and e power minus d by 2. Okay, so similar to what we had here, right? So this was less than equal to 3, so we had this 3 and then e power minus 2d. came from this V thing here. And so, okay, so this B is correct. So you have basically an exponentially decaying tail. Okay, A is like sub Gaussian. Uh, Option C and D say only if. So only if is not correct. If x1 to xn are independent, I mean, we don't require independence here because we're given that P satisfies this condition variance. So once we are given that condition, we did not require any independence at all here. Okay, it's to prove this thing, this variance is less than equal to this 4 expected value of gradient. For that, you generally require independence. Okay, but if you're given this, then you don't require independence any further. Okay, so now question 10. Right, this is the same question. Okay, so question 10 is nearly identical except that we have this condition. Instead of variance, we have entropy here, entropy of G square. Okay, and again we have the same, everything else is the same. So in question number 9 and 10, we are trying to see what happens when we are given these conditions. So okay, so again let y, again define y as e power lambda by 2 f of xn minus expected value of f of xn, right, as before, as in question 9. And again, this is basically our g of xn. So what this condition is saying, then that entropy of y square is less than equal to 4 times, and we have computed the norm of grad g square, which we can just copy from here. So it would just be lambda square by 4 square by 4. So what we had was lambda square by 4 into 4 into this. So lambda square, basically lambda square into expected value of y square. Okay, right. All right. So we had this, and so this was there in this week's lecture. So this is basically the Herbst's condition, right? So this was that Herbst's method that we take this, right, expectation of y square. This is less than equal to lambda square by 2 into 2, just to bring out this 2. Right, so we had this condition where if this entropy of e power lambda z by expected value of e power lambda z, if this was less than equal to lambda square by 2 into v, then we had the sub-Gaussian concentration. Okay, concentration meant like e power something like this, right? This was the tail bound. Okay, and this is exactly this thing. It's exactly this. So basically, we have a sub-exponential decay, and so A is correct. Uh, yeah. So for t less, okay, we are given, okay, for t greater than 1, B would also be correct because this is sub-exponential, this is sub-Gaussian. Then that's a good, for large t sub-exponential small, but we are not given that t is necessarily greater than 1, so B is in general not correct. Yeah, then C and D say only if, right? So again, proving this condition generally requires having independence across xn, but in this question we are directly given this condition. We are not, so we don't need to worry about independence at all. Right? So, okay, so that was the difference in question number 9 and 10. So okay, so now, okay, we are out of time, but let me just summarize what we have done till now. So okay, so in both last week's lecture and this week's lectures, what we had was, let's take this y to be this random variable z minus expected value of z. Okay, where z is this f of x1 to xn. Okay, and in the last week's lecture, we saw that if we have this condition that variance of y is less than equal to lambda square by 4 into v into expected value of y square. Okay, in this case, what we had was that, yeah, that basically gave us that this expected value of e power lambda by 2 z minus, sorry, is less than equal to 2 for lambda equals 1 by root v, right? And this implies this exponential tail or sub-exponential tail. Okay, so this is what we saw in question number 9. Okay, so this was like question number 9. This was last week's last lecture. This week, what we saw that if variance of y, sorry, if the entropy of y is less than equal to say lambda square by 2 into b, okay, lambda square by 4, lambda square by b doesn't matter, it's just constant. So in this case, we have that uh, less than equal to lambda square b by 2 for all lambda greater than equal to 0. Okay, so this gives a stronger bound on log momentum, and this gives sub-Gaussian tail, a stronger tail. Okay, uh, so yeah, it's entropy of y square here. So okay, so now right, so this is why this is the role played by entropy, that entropy, a condition on entropy gives you a stronger concentration compared to entropy of variance. Okay, right, and this is because variance is like expected value of variance is what it's like so both variance and entropy are what it's expected value of f of x minus f of expected value of x, right? So for f equals this square function which is convex, right, we get a variance, and then for f equals x log x, right, which is again a convex function, we get entropy, right? And if you see, and if you and we are okay, so we have a square here, but we are taking entropy of y square here, so again there will be a square if you take entropy of y and then square here. And if you plot these two functions, like if you plot x square versus x square log x square, where log is this natural log, you'll see that this x square log x square is has a more type, it's more curvy compared to this. Okay, so yeah, it's not exactly correct. So suppose this is x square, then your x square log x square would be this, right? So the x square log x square is a more curvy function, so it has like more curvature. So Jensen's inequality, Jensen's gap. So this is called Jensen's gap. Okay, that Jensen's gap would be higher. So you're up. So you're saying that that higher quantity is less than something, right? So which means you have obtained something tighter compared to just variance. So this is why you get a tighter inequality here. Okay. So again, overall goal of everything is to bound this moment generating function, right? And to bound this moment generating function, we just saw that one condition is if you can prove this, then for a particular lambda, you have a bound on the moment generating function, which gives you this sub-exponential tail. But if you can prove this entropy condition, then you have this bound on moment generating function for all lambda, and this gives you sub-Gaussian tail. Okay. And these quantities are important because, okay, why did we come to variance and entropy? These values tensorize. So variance tensorizes. What? Okay, so this was Efronstein. What that means is that now you have, if you want to compute variance of some function g of x1 to xn, right? It tensorizes. It means that you can just compute variance with respect to each coordinate while fixing all the other coordinates, and then obtain that variance as sum of, right, it was I equals 1 to n variance with, but after fixing the ith thing, right, of g of xn and then expected value. Okay, so this was Efronstein, that you can fix one coordinate, sorry, you can just fix everything except one coordinate and find variance with respect to that variable, with respect to that coordinate, and sum all of them. Okay, and that gives you the variance of the entire thing. So that this is something we saw last lecture, and using Okay, and this lecture we saw that this entropy function also tensorizes. Okay, and this was chain rule of, we proved this using chain rule of KL divergence. Okay, so this was something similar, that entropy, if you want to compute entropy of some random variable, and that random variable depends on many variables, so G depends on like x1 to xn. In that case, you can just compute entropy with respect to each, right? So fix ith coordinate, no, I fix everything except ith coordinate, and then take compute entropy, and then yeah, it's expected. Okay, right? And so this is why these inequalities are useful. That if you can, so now if you are given some function and it is a function of n random variables, you can, if you and you want to see if this bound holds, this entropy bound or this variance bound, you can break down the dependence. You can, so y is what, y is again here, y is e power lambda by 2 f of xn, right, minus expected value of f of xn. And so now you can in this f of xn, you can just fix everything except one, except ith coordinate, suppose, right? Compute this entropy with respect to that, and do it for every coordinate, and just, right? So you can basically do that, and after doing all that, you can just check if you get this inequality here. Okay, and this is how we basically prove log Sobolev inequality in this lecture, and this is how we prove Gaussian Poincare in last lecture. Okay, so yeah, so this is basically the summary of what we have till now. That okay, so again, using this variance inequality, we proved exponential decay, exponential tail um, for for it, for function with that bounded difference property. Okay, but that was just exponential. But we 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 can do stronger. We can derive a stronger result than that, which is that McDiarmid's inequality. And in the next week's lecture, we will see how we can use that bounded difference property and uh, this entropy relation to get sub-Gaussian concentration for bounded difference property functions. Okay, so that is what we'll see in the next lecture next week. And next week, so this will finish one module, and then this transportation module will begin, which is basically how to prove concentration inequalities using something called transportation method. Okay, so which will also again be introduced in the next week. Okay, so that's all I have to discuss. Thank you.